Okay, welcome to the part 2 of 3.1 molecule polarity. I did that again, molecule polarity. In this video, we'll be looking at second box of science understanding. The polarity of molecule results from the polar character of the bonds and their spatial arrangement. What you need to be able to do after this video, and we'll have a lot of practice with it in class, is to predict and explain whether or not a molecule is polar or non-polar given its spatial arrangement. Or you need to be able to draw that. Slides that I'll be jumping on from here is slide 7 of this slides. Alright, so molecule polarity. Okay, the polarity of molecule results from, firstly, the polar character of the bonds within the molecule, and we'll look at the video later together. And the bonds are their spatial arrangement. And the polarity of molecules is determined by 2 steps. Firstly, identify the shape of the molecule, and then determine the polarity of covalent bonds, and from there, the molecule itself. Now we'll look at 4 different examples there. So carbon dioxide, water, boron trihydride, BH3, and also ammonia Nh3. So they're just behind me. Now the structure is already drawn. CO2. When you use Vesper theory and do a molecular structure, make sure that pairs of lone pair of electrons are drawn. So each oxygen should have 2 pairs of electrons that are not for bonding. This oxygen as well. CO2 looks like that, and water looks like that. Why did I draw them in this way? Because bonds here, according to Vesper theory, all the bonds repel each other. So this double bond and this double bond, they repel each other as far away from each other. In this case, because there are only 2 pairs of electrons there, they would just become linear structure. And that's the name of shape as well, linear shape. On the other hand, in water, there's 1 bond, 2 single bonds are there, as well as 2 electron cloud that would push those bonds down. So even though there's nothing coming from, as in no physical bond there, oxygen would have this shape, the bent shape. V shape is the name given for this sort of structure. Structural shape. And you've got the BH3. Now, boron has 3 electrons in outermost shell. All those electrons are used up to bond with 3 different hydrogen atoms. This shape happens on the plane, on the same plane. So all the atoms there are on the same plane. Because of that reason, this is called trigonal planar on the same plane. Yeah. So it's flat, and boron doesn't have any lone pair of electrons. So yeah, that's it. BH3, just triangular flat shape. How about ammonia Nh3? Nitrogen has got 1, 2, 3, 4, 5 electrons. So one electron pair would be sticking up, which will push down the other 3 bonds. So it would have pyramidal shape. Because it's got triangular bottom, trigonal pyramidal shape. Trigonal pyramid. Alright, so shapes of molecules are done. Now what? You have to look at the bond polarity, then use that information to find out molecular polarity. Let's go back to CO2. Now, there are differences in electronegativity. Oxygen is a lot more electronegative compared to carbon's electronegativity. But in this case, the carbon is pulled to opposite direction with the same sort of force, which means that there is nowhere overall is negative or positive. Therefore, it is considered as non-polar. If it was as H and Cl, it's going to be linear, but it's going to be polar because one part of the overall, there's an overall charge difference. For V shape, if you add notations for delta positive, delta negative to show the bond polarity, there is a bit of overall difference there. Because of those lone pairs of electrons, you can hopefully see that the top half, oxygen side, is more electronegative compared to the bottom half. Because there's imbalance overall, it is a polar molecule. Okay? This is showing the bonds. This polar is referring to the polarity of the molecule. Molecule is polar. How about triangular planar? In all those three bonds there, boron is going to be delta negative, hydrogen would be positive, and in this case, because electrons in the this molecule would be pulled towards center with same force. That's why this is also non-polar. What do you think of nitrogen and hydrogen? Nitrogen would be delta negative, hydrogen would be delta positive in each bond. Is there any imbalance overall? I can see the overall charge difference. So top half, nitrogen side, because of that electron as well, it's going to be more electronegative. So that's going to be overall negative. And the bottom half, the hydrogen legs, I guess, that would be more positive. Therefore, this is polar. Okay? So that's how we look at them. Okay. In class, you'll be looking at something like this, and we do more examples. You will be using next slide to look at the shape. You will draw them, you look at each bond and determine the polarity of each molecule. Here's a list. Oops, dropped my mouse. And so that's the list. And going back to the next one. We'll also be looking at polarity of molecules for SO2 and SO3. It's a bit unique, so I'll just introduce that. And there's a question in textbook. It's not gonna be tested, but it's very important for you to know how to draw them, because they go through what's called expansion of octet. Octet usually means 8, but you can fit more than 8 electrons for some elements. So we'll talk about using those too, and we'll do that in class. The polarity of molecules can be defined, defines the strength of secondary interactions. This idea leads to the next subchapter. So yeah, so things like hydrogen bond can be covered later. If you have, what I wanted you to also know is that even if a molecule has polar bonds, that doesn't make polar molecule. Some polar molecules can have non-polar bonds, and or vice versa. Okay, you could have polar molecule from polar bonds only, or a non-polar molecule from polar bonds only. Comparison, well, if you compare H2O and CO2, you could see the good news. So they are polar bonds, but the molecular polarity is non-polar, whereas water is polar. That's really that. we'll be looking at the questions in the textbook from that. So we'll be looking at page 102 to 104. And that's really it for this subchapter. So part 2 only. We'll be moving on to 3.2 after this video. All right, see you then.